Hi, physics. Mr. Janowski here. I think this is part 3 of the chapter 4 slides. It's either part 3 or 4. Um, so, yeah, just quick, let me remind you of the resources that you have available to you. Although, if you're watching this video now, you are probably fairly aware of the resources that are available to you. But yeah, on Google Classroom, there's always the slides, the homeworks, and the homework solutions. So if you're ever doing a homework and you're getting stuck, take a peek at the solutions and see how I did that problem, and then that will get you unstuck. I also have a YouTube channel, which you know because you're watching one of the videos now. So there are slide summary videos like this one, and then there are also homework videos, how to do a particular homework problem. So there's a link to that there. I, of course, am also a resource to you. So if you have questions about the material or anything else ever, you can email me, you can send me a Google Hangouts, or you can just come to my office hours on Wednesday from 10 to noon. And finally, another resource is each other. So yeah, there are lots of students taking physics now. So if you're having trouble with the homework, it's likely that someone else is also having trouble. So contact them and try to work on the things together. You know, have a little Google Meet, start a Jamboard, and then work that way. So the do now stuff. So back to these motion map problems. So yeah, remember the car is going from left to right. It's dripping oil at a constant rate. So if we're looking at this, the location of the drops gives the displacement. So where the drops are tells you where the car was. The spacing between the drops gives you the velocity. So when the drops are close together, like they were here at the beginning, the car had a low velocity. Towards the end, the drops are further apart. So the car had a higher velocity. And how the spacing between the drops changes, that gives you the acceleration. So notice the drops keep getting further and further apart as we go left to right. Well, what that's telling you is that the car was accelerating to the right. So displacement, velocity, acceleration. These are three quantities we're going to be very interested in for what we're doing today and for the rest of the chapter. So symbols and units. What is the symbol for displacement and what are its units? X if it's horizontal displacement, side to side. Y if it's vertical displacement, up and down. And the units for displacement will be meters. What is the symbol for velocity and what are its units? V for velocity, that's awesome, that makes perfect sense. And its units will be meters per second, m divided by s. And how about acceleration and its units? A for acceleration, and the units for acceleration will be meters per second squared. So m divided by s squared. And then the last do now question, when is an object in free fall? An object is in free fall when gravity is the only force acting on it. So no normal force from your hand, you're not holding it. You're ignoring air resistance, either because you're on the moon or something and there's no air resistance, or you're in a giant vacuum chamber. Or the thing you're dealing with is so massive and it's not moving fast enough for air resistance to actually matter very much. And so there's a little air resistance, but you're saying it's very small, so you're just saying it's negligible. You're ignoring it. We do that a lot in physics. So yeah, that is when an object is in free fall. And when an object is in free fall, it will accelerate downward at a constant rate. It won't move downwards with a constant velocity. It will accelerate downwards at a constant rate, a constant acceleration. So here's a new term, or new thing. Little g. Little g is equal to minus 9.8 meters per second squared. So this is the acceleration due to gravity near the surface of the Earth. So little g is NA. It is NA. Little g is an acceleration. So you could write A sub gravity, the acceleration due to gravity, but that takes too long. You could write A sub g, but even that takes too long. So just write little g. This is something we will use so often that we should just all agree to do it this way. It's fastest, right? The acceleration due to gravity has a little g. It's got to be lowercase. Again, it's minus 9.8 meters per second squared because by convention, up is positive and down is negative. Things will accelerate downwards, so g is a negative number. So you should know this number, burn it into your brain, do not need to look it up. We will use this number so much that you don't want to have to look around to find this number. Just have it handy in your brain. And frankly, whether you want to or not, you will memorize it because we will use it so much that you'll just memorize it. So little mathematical point here. Is g equal to 9.8 meters per second squared or negative 9.8 meters per second squared? And the answer is, it depends on how you're doing the problem. So you can do the math and set the problem up in a certain way and use the positive number. But for this chapter and the next chapter, use the negative number. It's minus 9.8 meters per second squared because it's going down. So we go with that. So here's a situation. You were standing on top of a roof, and maybe you're kind of leaning over the edge. You're going to throw a ball straight up in the air. It's going to go straight up, and then it's going to come down. And on its way down, it's going to miss the edge of the roof. So it's going to go all the way down to the ground. So we're going to look at the ball's position, where it is, displacement, and also its velocity, represented by the blue arrows, and also its acceleration, represented by the red arrows, at all the different points in time. So when we do this, there's a couple of interesting things to notice about the velocity. So again, the velocity is the blue arrows. And the magnitudes, meaning the size of the blue arrows, and the directions will change over time. So at the beginning, at t equals 0 seconds, the ball leaves your hand. So it's going up. And the velocity is, let's say this is medium size. And then a little while later, the ball is still going up. So the blue arrow is still up. And now we have a small arrow. And then at t equals 2 seconds, there is no blue arrow. It's not that I forgot to draw it. It's that there is none. Because when the ball is at its very highest point, it will momentarily be at rest. It will have no velocity. And then after that, you have a small blue arrow going down, and then a medium blue arrow going down, and then ultimately a big blue arrow going down, because the ball is gaining velocity in the downwards direction. Now, something to point out here. If you compare the velocities at t equals 0 seconds and t equals 4 seconds, so right here and right here, what do you notice about the blue arrows? Well, they're the same size. So they are equal in magnitude, that means they're the same size, and opposite in direction. So that means the ball is moving just as fast downwards here as it was moving upwards here when it's at the same height. And the same thing is true at 1 second and 3 seconds in my little drawing here. So small blue arrow going up, and when the ball is at the same height going down, you have a small blue arrow going down, exactly the same height. So what we know from this is that the downwards motion mirrors the upwards motion. So this is something that when you're doing the kinds of problems we're going to do, they're called kinematics problems, it's often a useful thing to realize that. The downwards motion mirrors the upwards motion. So if the ball is at one height on its way up, and later it's at that same height but on the way down, its velocity will be the same size but in the opposite direction. That's true at least if it's going straight up and straight down. Different if it's going in 2 dimensions, but we'll deal with that next chapter. And now we look at the magnitudes of the red arrows. And notice that the red arrows always have the same magnitude, and they always have the same direction. The red arrows are always pointing down. So this is a little bit trickier than the other thing. So the ball will have a constant downward acceleration from the moment it leaves your hand. So at t equals 0 seconds, the ball has just left your hand. It's moving up because the blue arrow is up, so its velocity is up, but its acceleration is down. This bothers many people when they first start learning this, that you can be moving in one direction and accelerating in the opposite direction. It's a little weird to think about until you really think deeply about how motion works, but that's just completely true. So the ball is moving up at t equals 0 seconds, but it's accelerating down. At 1 second, it's still moving up, but it's still accelerating down. And then notice at t equals 2 seconds. So at t equals 2 seconds, no blue arrow, no velocity. The velocity is momentarily 0. The ball is just for a moment at rest, but it is still accelerating downwards, which means you can be at rest, but still accelerating downwards, which is another thing that bothers people. It seems a little bit weird. And then after that, the ball continues to accelerate downwards, and now its velocity will be going downwards. And most people are okay with this. It's moving downwards, the blue arrows are pointing down, and it's accelerating downwards. So it's going faster and faster downwards as time goes on. So, yeah, that's an important idea. The thing with the acceleration being constant. So, before you learn physics, it is common to think that gravity will do something to the ball on the way up, and then maybe it stops or does something different just for a moment when the ball's at the top, and then it will do a third thing when the ball's on the way down. And that's not true. That's not how we think of this. Gravity is only doing one thing the entire time. From the instant the ball leaves your hand until it eventually hits the ground, which is not actually even pictured in this, this image here. for that entire time, gravity is accelerating the ball downwards. Its velocity is changing. Its velocity is going up, and then it's zero, and then it's going down. But its acceleration is always going down, and it is always the same amount. Tricky idea. You've got to do it a few times until you wrap your head around it, maybe. So now we start the kinematic stuff. So the kinematics equations, these are the set of equations that let you calculate several different unknowns. So your unknowns could be displacements, velocities, accelerations, possibly time, for any object that is moving under constant acceleration, which is underlined because that's important. The kinematics equations only work when your acceleration is constant. So if we go back to this previous image, when the ball is in your hand and you're in the process of throwing it upwards, there's more than one force on the ball. There's gravity downwards. There's a normal force from your hand going upwards. So the acceleration won't be constant throughout that part of this thing. But the instant the ball leaves your hand, no more normal force. There's only gravity acting on this ball. So from the moment the ball leaves your hand, it's in free fall, only gravity, so constant acceleration downwards. Then the ball goes up and it comes down. And then we assume that eventually the ball will hit the ground. Well, the instant it hits the ground, it's going to get another force from the ground. There'll be a normal force from the ground. That's going to change the acceleration. So you have to stop your kinematics equations the instant before the ball hits the ground, because the kinematics equations only work when the acceleration is constant. So that's a key idea. So yeah, I'll go through this stuff quickly. Here are your kinematics equations. You don't have to memorize them. I will always give you these equations. These are on the footers of every homework. They will be on the footer of the study guide. And when we ultimately get to the test for this chapter, they will be on the footer of every page of the test. So you don't have to memorize them, because physics is about understanding things. It is not about memorizing things, which is something that I love about physics. Another part of doing kinematics equations is what's called the variable bank. So that's this stuff over here along the right edge. So in a kinematics equation, or in a kinematics problem, there are going to be 6 different variables that we care about. X initial, X final, so that's the displacement. V initial, V final, those are the velocities. A for acceleration, and time. So we want to figure out these things. Some of them we will know when we're getting started, and we have to figure out the other things, is usually how it works. So some things to point out here. Notice if you look at the kinematics equations over here on the left, some of these things contain delta x. So 1, 3, and 4 all contain delta x. Notice your variable bank does not contain delta x, which may be a little confusing until you remember that delta anything is the final thing minus the initial thing. Therefore, delta x just means x final minus x initial. So even though delta x is not explicitly in your variable bank, it is in that sense. So what that means is I could have written, for example, the first equation, instead of having delta x equals on the left side, I could have x final minus x initial on the left side. Some physics teachers would do it that way. That's fine. But that takes too long. So I just write delta x. That's how you do it. Another little thing is t should really probably be delta t, because your problem will always start at some initial time and it will always end at some final time. However, every problem I give you, I'm going to set it up so that t initial is just 0. And if t initial is 0, well then follow this logic. Delta t is equal to t final minus t initial. But we're going to make t initial 0. So that's equal to t final minus 0. So that's just equal to t final. So you only have t final in the problem. If you only have t final, you don't really need to have the final. You don't have to write t sub f. You can just write t. There's only one t in the problem, so you don't need the subscript for it. So that's that. And then point number 3 is I have written these equations with x's. So delta x equals, there's no x in 2, all this stuff, blah, 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 plus 2a delta x. And then finally delta x equals. So I've written them in x's, but some of our problems won't be horizontal. They will be vertical. So in those problems, just swap out all of your x's and plug in y's. And that works perfectly fine. So finally, here are the 7 steps of my 5-step kinematics problem procedure. So all year long, I'll go through this quickly, but we're not actually going to do a problem here because I have another video of me doing the problems, which I'll put a link to that in the description. So let me just quickly tell you what the steps are, and I'll explain them in more detail in that other video. So before you even get to step 1, do step Ask yourself, what am I solving for, and what are its units? So step basically means, do I understand the problem? What am I actually trying to find? What units do I expect? So always do that. For kinematics problems, for any other problem. In physics or math or even English, whatever the subject is, if you've got to write an essay, read the question carefully and just make sure you have a clear understanding of what is being asked of you. That's always important. And then step 1 all year long will be to make a sketch. Physics teachers love sketches. So any kind of problem we do, kinematics, force, momentum, energy, anything, step 1 will always be make a sketch. After that, in a kinematics problem, you have to fill out your variable bank. So you look at these 6 numbers here, and some of them you're going to know, and so you write in their values, and some of them you aren't going to know. So if you don't know it, you write a question mark for the unknown thing. Step 3 is basically just do step again. Circle the unknown in the variable bank that you're trying to solve for. So it's a little bit redundant, but I like it because it leads very nicely into step 4. Now, step 4 is pick an equation. So you have to look at your 4 kinematics equations, and you have to pick the one. There may be more than one, depending on the problem. That could work. But pick one that has the unknown that you're looking for. So the thing you just circled in step 3, you have to pick a kinematics equation that has that thing in it. If it doesn't have that thing, that equation can't solve for the thing you're looking for. And the other condition is you have to avoid any other question marks. So if you have 4 known things and 2 question marks in your variable bank, you have to pick a kinematics equation that A, has the one you're looking for, and B, avoids the other question mark if there is one. Because it's a rule in math that if you have 2 unknowns in one equation, you can't solve for it. That's just how math works. And then step 5 is do the math. And there's a particular style I will recommend for doing the math. And I explain all that in the other video. And then the last thing is step So this is bookends nicely with step Step means, does your answer match your step Because in step you said, all right, what am I looking for? What units do I expect? So make sure that you have solved for the right thing and you have given it the right units. You lose half a point if you don't have the right units. And then does it make sense? So if it's a velocity, do the bloody cheetah and figure out, okay, what is this velocity that was in meters per second? Well, what is it in miles per hour? And then ask yourself, based on your real world experience, is that a reasonable velocity for the thing I'm dealing with? If it's a time, then think of, does that time make sense? If you throw a ball up in the air and then catch it, and the question is, how long does it take for the ball to go up and come back down? And the answer you get is 500 seconds. That's not very reasonable. You can't throw a ball so that it goes up in the air and doesn't come back down to you for another 500 seconds. So yeah, that's what the doesn't make sense part means. So that's it. That is the 7 steps of my 5-step kinematics problem solving procedure. So again, I will link the video of me actually doing one of these problems as an example. And I hope you found this video helpful.